Well, it's a pleasure to introduce Sergei Gukov. He's going to talk about mathematics as a game. Floor is yours.
Yeah, thank you very much. So first, I want to thank organizers for inviting me here and more importantly for organizing this meeting. So hopefully jointly going forward in next future years, we'll have sequences of this meeting. So alternating between IMSA, CalTech, and perhaps other locations. So stay tuned. Hopefully we'll do more of it. So I'll tell you my personal perspective on the relationship between mathematics and machine learning. Um, my own background is very far from this area. I was originally trained in more geometric areas of mathematics and was Yale's postdoc working on mirror symmetry, special holonomy manifolds, then moved closer to quantum algebra and quantum knot invariance, things like that. And 5 years ago, when AI sort of started influencing various areas, and you probably can guess that I like building bridges, I asked myself, is this another possibility or opportunity for us to build a new bridge? Honestly, I was hoping that the answer is that there is nothing substantial, it's just a hype, and I would, learn it and prove to myself I don't need to learn more. It turned out that I was wrong, so I did some first steps about 5 years ago and learned that on research level problems, AI models, even back in that day, can do 10 times better than me as a research mathematician. And that was the point where I saw, okay, I cannot ignore it. I have to actually invest more effort. And obviously, if we scale, we can do 100x, 1000x, so we can continue improving it. And the way I see it now is that in the future, it will be basic literacy. Very much like one cannot become a professor in university without knowing LaTeX, how to write papers in LaTeX. It's not a formal job requirement, but it's something that we kind of have to know, otherwise we're way behind. Same is going to be with AI. So that's basically my present. So with this, again, I'm not an expert on many things,
then again, cheap down some kind of music.
Yes, and?
They're writing 10% more.
Oh, that's, well, but they still have somehow. That's a good point, yeah. You can still do good mathematics, but then you have to be exceptionally good. Again, at the level of Cliff and Harris. All right, so then in the first 10 slides or so, I'll try to clarify what I am going to tell you about and what I'm not going to tell you about. About a year ago, after having already some experience with AI and mathematics, I joined a company in Silicon Valley trying to train AI systems to win international math Olympiads. So this turns out to be a very smart move because just a few months after I joined, in October 2023, there was a 10 million prize put out for precisely this sort of challenge. So shortly after, Wall Street Journal published this article, answer 6 questions. This refers to IMO questions, and win $10 million. In my opinion, this is a pretty good way of making money compared to millennial price problems where you can have to solve one much more substantial problem like Riemann hypothesis or Navier stocks just for 1 million. And here you just answer 6 questions and get 10 million. Anyway, I won't be able to tell you what we're doing because it's a private company. I signed all kinds of NDAs, so I cannot speak about it here. But what I can tell you is that it's very promising and relatively easy, in my opinion, task for AI. In part because when I was a kid, I liked Olympiad myself, and I actually trained for IMO and many other Olympiads. And the process was very straightforward back in the day. I was in Russia at the time. So you would be excused from all school lessons. That was fun part. You would get some special paper from government or something telling you that you can skip music, literature, whatnot, and just solve math problems. And what we did, we basically on the course of a year learned 25 strategies how to solve math problems. It was like a boot camp. You basically solve hundreds of problems, and it becomes like riding a bicycle. After hundreds of problems, the next one you see is just yet another. So it's very much like AI learns to solve problems. It's a training. At that point, it wasn't human. And I continued throughout my career. I trained American teams a lot. So my feeling is that this year is probably last time I'm training a team, but a team of robots basically to learn AI more problems. And I don't know if it will happen this year. So this 10 million prize put out by XTX company in London, I don't know if it will be taking this year or next year, but projection is that yes, within a couple of years it will be done. And here you can see on Kalshi there is people like betting what's the rate that it will happen in the next 2 years. This snapshot was taken in March or April of this year, yeah, March 28th, then April 15, and so on. That shows kind of evolution. So it will go up, and at some point it will just skyrocket, meaning that yes, we did that. Anyway, I'm not going to talk about this level of problems here because these are easy, and just like for a team of students, there is so much literature, so many other problems to train on. Same for AI. So there is a lot of data or data sets which can be used for this sort of training. These are relatively easy problems, so that's not what I'm going to be interested in. I'll tell you, yeah, so trying to narrow focus now from computer science perspective. So this is one of the first plots we probably see, or Venn diagrams about different areas of machine learning, AI, how they fit together. And when I saw this kind of plots when I was learning the subjects, I always thought about this reasoning, artificial intelligence, as kind of like philosophical, and I thought, okay, I'm very country guy, I'll probably stay just with machine learning. So actually these days, kind of questions I think about, and hopefully in this talk there will be some hints why, they involve actual reasoning and artificial intelligence, and that's, so I'm surprised that after 5 years I sort of migrated from machine learning to AI. Right, another thing that so this is my own presentation of rough division of machine learning into standard categories, just to sort of outline what I want to do. Three very traditional areas that are usually specified involve supervised learning. This is where your data is labeled. Unsupervised learning, that's where your data is unlabeled. And reinforcement learning, which is basically AI playing games. So in supervised learning, things are much easier usually compared to the other groups. It's typically some classification task or regression. Unsupervised learning is usually a typical thing, is something like K-clustering. And reinforcement learning is playing games of chess. Or here in my case, this is Moonlander, and those of you who actually had CS course on AI or machine learning probably had to train an agent to do something like this. For example, safe landing on the moon. It has to be on a reasonably flat surface and kind of with a slow speed. So this only takes 100 lines of code, and of course there are environments now in Gym and whatnot that allow you to realize it. So this is actually like reinforcement learning 101. And as you can guess from title of my talk, I'm going to be focusing some very concretely on this domain of AI or even machine learning. So I'll be very, very specific, and I'll have nothing or little to say about other ones. I mean, they're cool, they're exciting, but most of my mission in this talk is going to be on reinforcement learning because this is synonymous to gameplay. Okay? So why is that? There are different bridges, again, speaking of building new bridges, where mathematics and machine learning or AI in general come together. One can try to use mathematics for AI to make AI more understandable, more explainable. This is what some people call white boxing of AI, developing new algorithms, and that's where mathematical ideas sometimes are quite useful. Then there are various combinations of AI with existing proof assistants based on lean cogs, set solvers, all kinds of standard tools. And that's its own kind of area, which hopefully will lead soon to auto-formalization. That's something that many of us are looking forward to. Yeah, that's I would say yet another sort of bridge or interaction of pure mathematics and AI, which currently works reasonably well at the level of undergraduate curriculum or high school curriculum. You can build systems which complete, it's like auto-completion in natural language. They auto-complete proof for you, but of a fairly simple statement. And of course, it's only a matter of time and improvement that this will reach graduate level and then research level and so on and so forth. And then there are people who use machine learning for solving research level math problems. So this is where I myself started my journey, and most of my talk will be sort of you'll see roots in this area. And again, they can be of different kind. For instance, you can generate a lot of synthetic data, throw it at supervised learning, ask algorithm to do some classification or learn unknown function and discover some new relation, make a conjecture. You can also use reinforcement learning, something I'm again emphasizing that is the main part for me, to prove or disprove some old standing conjecture if you need to find an instance of something that's hard to find. Again, that may be hard for human, not so hard for AI, and so on. So I gave versions of this talk, and some of you who've seen my talk in the past 5 years probably even seen this slide. And I used to say that, yes, these areas, they clearly interact with each other and they're kind of distinct, but by trying to learn what works, what doesn't work in AI applied to mathematics, we also learn more about algorithm development. So clearly there is interaction, and there are many ways that they feed into each other. Today, I actually think that main challenges in all of these three types of bridges or areas are actually the same. So I don't actually distinguish between using reinforcement learning to disprove, say, Poincare conjecture in dimension 4, which is closer to my field, like dimensional topology, and try to develop very sophisticated AI proof assistants. Why? Because if you have a conjecture that you want to disprove, you basically have to, it's kind of search process. So you have to find some rare instance of a certain thing. So you make various steps, and your goal is to find, I don't know, something very cool that you're looking for. So a counterexample to Poincare conjecture. But this process, viewed from a reinforcement learning perspective, is exactly the same as if you have a hypothesis and a goal statement, and your job is to find a sequence of lean steps that connect H to G, or take you from A to B. So from a REL perspective, if I'm trying to prove Riemann hypothesis, the process is not very different from disproving Poincare conjecture by looking through knots and things like that. Because our job is just to find a rare sequence of moves which achieves the task. And we always have some kind of H, which could be the unknotted circle, and G, which could be some complicated knotted diagram, but it would be also the hypothesis and the goal for Riemann hypothesis. So from a REL point of view, all of these problems are actually almost identical. So in some sense, not only they feed into each other, indeed, what we learn on one is useful for the other, but I want to make a point that they're, for reinforcement learning, they're essentially the same. By the way, feel free to interrupt me at any point, ask questions.
Well, for the first one in red, for instance, you pulled the image not using only reinforcement learning, but actually the problem one in green. So then in this case, we will still be that similar. I believe the answer is yes, but you're talking about reinforcement learning. You have a purely supervised learning, for instance, from proof of the formalization. I mean, I'm not saying it works, I'm just saying we tried as well.
Yes, it's possible to try it. So the reason I want supervised learning is good when you have many cases to train on or label data which you want to approximate and so on. So this is important because in approaching it with reinforcement learning, because we don't have that many instances of Riemann hypothesis or that counterexamples
for the
one for
the Riemann hypothesis, other finding counterexamples to other problem where some such of data or you could create some synthetic data, and probably the same for formalization. You can probably informalize data, yes, informalize data, and then train something to formalize even crappy data and try to do something even better after.
Right.
I'm just doing I'm doing the devil's advocate, obviously, but
yeah, I mean, I think that, so, yeah, so all tasks which, right, so that's why I'm trying to specify the problem. I'm not trying to solve problems which are research level or develop, what my goal of the talk is develop algorithms, and my goal is to explain why there is a need to develop something new for hard, really hard research level math problems. Because I want to ask mathematicians, not just to say that, oh, this is cool, they got 10x improvement. I want us to go to New York or whatever, Wall Street Journal, and say that they actually achieved something. So really build for this. In my experience, again, I'll be glad to discuss this a little bit more in detail, is that models which, so we need to be able to solve problems such that their analogs are not solved currently. So that requires typically, what works well in that domain is either generative kind of AI or reinforcement learning. Both of them are somewhat close to each other, rather than many.
Yeah, sorry, I was talking about more generative AI. So then they are trying to supervise learning in many cases. So
that's right. Yeah. So that would be great territory. Yeah. So in this talk, I prefer to actually, I was thinking of saying something about generative aspects, but to make it cleaner, I put it in RL. Another reason is that out of these three big chunks of machine learning, reinforcement learning is usually considered the hardest. It's definitely, if we are like learning in CS 101, the reinforcement learning algorithms, they're usually very finicky. They require more practice, and like there is more going on with adjustment of these algorithms to make them really work. So in some sense, this is also more interesting from just AI perspective. Like again, thinking about white boxing it, what should be the strategy? How do we do it? And again, I consider myself as like experimental mathematicians when I come to this area. I actually want to get the job done. So it would be good if somebody told me how exactly to adjust hyperparameters and some, I don't know, a reinforcement learning algorithm to make it work. So that's
the space of move for the space of actions in the counterexample is really huge, right? So you need to discretize something like that.
That's exactly what the rest of the talk is going to be about. So yeah, so this is a great question. In some sense, this is I'm going to try to unpack precisely this question and break it into all kinds of subsets. Yeah. So focusing, so defining the problem, focusing on very high level math problems, something that hopefully will disprove. My benchmark is let's try conjectures which were open for at least 30 years. Something hard, something that will move the needle. And so research level math and RL, just to make it kind of self-contained, because even here I think I'm going to run out of time. Okay, so naive strategy is very simple. You can formulate many math problems. Again, my original area is, before I came to this, was in quantum topology, where people study these knotted diagrams a lot. And typical question, which sounds very simple, is to decide if this diagram is equivalent to this diagram when you're not allowed to break the string, but you're allowed to basically do all three-dimensional moves that don't change it. So here you can probably try to do this exercise with a naked eye, because complexity measured in terms of number of crossings is relatively small. But if you go to more complicated diagrams, it quickly becomes more interesting. And in topology, we care about much more complicated diagrams. You probably have seen this in previous talks, and I'll have something later to show you. So this is, for example, 30 crossing example. You already see how your eye is no longer as trained to decide whether this is trivial or non-trivial. Sometimes in the past I would poll the audience. I'm not going to do it here. I'll ask you some other questions. So anyway, the point is that you can formulate this as a game, trying to train RL to reduce it to trivial unknotted circle, and then it basically is very much like game of chess. I think this is a good example of a problem. And again, I'll use some examples in this talk from my own work, and they may involve knots and things like that. This is, to me, this is at this point is just an instance of how AI can be used, and my main interest is in fact in algorithmic perspective. What works, what doesn't, and why. So how can we improve it, and so on. Even if I'm going to use examples from knot theory, don't worry about it. If you like knot theory, that's fine. If you don't, again, it's not important to me in this stuff. Okay, so in fact, this problem of knotting, unknotting is actually relatively good. Naive approach would be that, oh, it's quite simple because speaking of space of states and actions, it actually has three types of moves. In knot theory, famously called after Reidemeister moves. So this is basically three moves, which is like moving your joystick left, right, and up. So it's more like a parry game. So it's not really a chess game. In chess game, you have so many moves, pawn moves different than knight and so on. Here you have three basic moves, right? It's almost like you're playing checkers, some more primitive game, not really chess. So therefore, you would expect that this unknotting game, trying to recognize whether the knots are trivial or non-trivial, should be fairly simple. And that's the project that, in some sense, brought me to this field together with Fabian, Jim, and Porter. So we represented complicated knotted or unknotted circles as braids, so as braid words. Then already at that time, various LLM type models were coming out and so on. We were already having this development where natural language and anything that involves words was kind of easily interpretable to AI. So braid words, of course, is just an instance of it, and things worked out really well. So in the paper, we have lots of graphs which look like this. This is typical thing that I thought is what, as a student in reinforcement learning, I should bring to my teacher, because it basically shows that upon training over some number of epochs, performance improves. It quickly approaches 100%. That's what we always want to see. So this is the main message I saw 5 years ago in this graph. There were a couple of other messages that maybe I'll explain in a second. These days, when I look at this graph, I see something different. I'll come back to it. So my previous take from typical books was that this is showing success story. I'm actually not sure anymore, but again, the reason I'll try to explain later. So this shows performance of a very particular AI architecture called Reformer. So I'm sure most of you know what GPT stands for. So that's based on Transformer, and Transformers these days are very popular. So Transformer is an architecture which is very sophisticated. This is a simplified version of it from original paper called Attention is All You Need. So it's based on this attention mechanism. In fact, there are many more building blocks here, such as very interesting versions of Fourier transform and all kinds of things. And Reformer is actually something much stronger. So Reformer, as the title of this paper suggests, came out a couple years after. It's even better than Transformer. So we were almost finishing a paper back in the day. This thing came out, so we felt obligated to try the coolest, most recent thing. And what the graph on the previous slide shows is that it actually performed just as well as feed-forward neural networks. So to us, it was interesting that the coolest thing, which is even more sophisticated than Transformer, did just as well as feed-forward neural net. So what this means is that this unknotting problem, the game of recognizing knots, is easy for AI. It doesn't matter which architecture you use. You can use super sophisticated thing, such as Reformer. I don't know how many of you have heard of it, or just feed forward. So it's doing just as well. But another thing I have to clarify is that the graph I showed you was actually precisely from the supervised learning category. So it was training AI to tell us, this machine learning model, to predict whether, given the braid presentation of a complicated knotted diagram, it's non-knotted or knotted. So it was basically this recognition task, decision problem. It wasn't RL, so I'm not actually fulfilling my promise. But of course, in this paper, we also try to play the game. So teach reinforcement learning to play the game. And here we come to our first lesson. So this is the models that really take complicated knotted diagrams like this one and try to ask, can I connect it or play the game where the win state is a knotted circle? Okay? So not only predict, but actually execute the moves. So this is more delicate. This is where reinforcement learning is more subtle in training compared to supervised or unsupervised learning. And that was the outcome, again, back in the day, when we were playing this game. As you can see, it can go up to grade length of 100. And this is definitely way above what I could do as a research mathematician. So typical number of crossings, I'll come back to it, where we operate as not theorists, as about 10, 15, 20. So this was 10x, and actually this is on log scale, so it's like pushing us to stratosphere in terms of what I could do with paper and pencil. And what I could see back in the day from this graph is that, again, there is blue set of dots. I'll explain what this is, associated with this trust region policy optimization algorithm, which goes to accuracy of 100%. So again, I would take this as a success story. What I want to focus on now is something else. So in machine learning, as many of you know, typical comparison benchmark is to compare these algorithms to random walker, because that's how we initialize usually reinforcement learning agents. We just tell them to make these moves at random, and then they start improving. So random walker on this graph is a set of green dots, and of course, it just plummets. It doesn't perform very well, especially if you increase number of the length of the breadboard, it performs poorly. But then there is yet another guy here represented by orange dots. So this is A3C algorithm, and again, I'll talk about all of them at some time, which does something interesting. So at first it shows a kink. It starts going up, very much like the successful guy, but then it goes down. Okay. So one thing that now these days I see from this graph is that I see that some reinforcement learning algorithms work really well, some don't. And therefore, a question becomes why? Is it specific to algorithm? Is it specific to a problem? And we actually need to understand this kind of question so that we can, when I have my next problem, something more serious, I can actually put a custom-made algorithm that works best on that problem. So if I'm not understanding why this happens, I'm searching in the dark. So this has two lessons. Do you have a question?
Yeah. You can finish.
Yeah, I'll finish the sentence, I'll come back to it. So this has two important lessons, which, again, back in the day I didn't appreciate because I saw that this is a success story. Now I see something different here. First of all, it tells us that it is extremely important if we want to solve an interesting research level math with AI to experiment. Even experiment with off-the-shelf algorithms. Take something that has already a name, A3C, TRPO, and I show you a couple more, and try all of them. Just experiment with the existing ones. Because we'll find a non-trivial distribution. We'll find exactly this sort of story in every single problem, that something performs better, something does not perform better. So we have to have differentiation. Second lesson that we learn from here is that if off-the-shelf algorithms work differently on a given type of problem, most likely the optimal algorithm for that particular type of problem is not even off the shelf. We have to design it ourselves. And this is cool. This is where it feeds back into AI, but also informs us on what works well, what doesn't. Yeah, sorry.
So I don't know anything about knots, but my naive understanding or thought would be like, okay, if the braid length is getting longer, like the sort of complexity is increasing. So, I mean, the random walker sort of shows more what I would expect, but as the complexity goes up, performance suffers. But I guess, like, the TRPO, the result from that, is it suggesting that there's some high degree of redundancy, like in the knot, or like some key structural things that just don't matter, even if it's becoming larger and more complex ostensibly?
So in other words, you're asking, why is this blue guy going up and not going down? Maybe slowly, but still. Can I interpret that way? Or?
Yeah, like the complexity of the knot, even though it's increasing, the relevance of that increasing complexity plateaus, maybe. Like why Is there a
I
thought
don't
why
have
that-
an answer to this. So yeah, this
But
is
you are guessing, you have a guess, no?
well, yeah. In the paper we propose various scenarios why this may be happening, but this is an interesting question because this way we're learning something about distribution of knots, which actually mathematically we had no clue until this machine learning came about. Until 5 years ago, we had no idea what space of knots is like. So, for example, asking in the next project, I'll show you that we're asking what fraction of, I don't know, 40 crossing knots is slice. So this is also yes or no decision problem. And even best mathematicians, they could not predict, or they didn't have a clue or a guess. So we didn't know distribution of knots in terms of all kinds of properties or complexity. So that's one thing. And here it's interacting with another black box, which is what TRPO does and why it's better on certain tasks and so on. So in some sense, we're putting two unknowns in the equation, and that's why maybe I'll use your question to, again, emphasize another point that it's important to experiment with algorithms, because if we have two unknowns in the equation, it's hard to extract information. But if one of them becomes a variable, such as algorithm or architecture used by ML, we can bootstrap the properties of the data set we're learning, if that's also a mystery, and that's the case here. In any case, we don't have a good answer, but one funny scenario that we propose is that it's like a game of chess. If you play with stronger opponent, which means higher number of crossings or length of rate, it becomes better. I don't know to what extent.
No, yeah,
that's a good analogy.
I mean, it's wild. I get it. I don't know if it's suggesting some kind of like emergent property of those knots or some, some stability, if you will, like after a certain amount of complexity. Stability meaning like if it's even solvable, sort of, it just goes against what I would expect.
I agree. Yeah, I think that's a surprising result, and we didn't come back to it over years. I'm sure it's good to look into this more. Yeah.
Maybe you do it again, just try it again to see if it comes the same.
Well, if you try it again, it will surely come the same. By the way, another thing that I want to emphasize is that anybody can. So even though now I'm working with, I spend half of my time in Silicon Valley and work with companies, I think it's extremely important that we all have open source code. So everything that I'm going to tell you about is open source. And I think every talk of this style should have a social residue. So no, I don't think I have it here, but on later slides, I'll have GitHub or downloadable code. So anybody can go and download it and reproduce it.
So the TRPO does not improve itself with the years?
At least the model that we trained, it is what it is. So if you try to run it again, it will show the same behavior. But of course, what would be good is to actually try to dive deeper and do more experiments with this and understand what's happening. And we can use same model or train another one and debunk this question, which is interesting. But I think the consensus here would be that what we definitely read from these experiments is that this particular what seemed like high-level math problem turns out to be relatively easy for AI, surprisingly, because indeed there is some structure, and I would expect that the graph, even with a good performance, should have this kind of form. The fact that it improves shows that there is indeed some substructure that it quickly learns, and it probably reaffirms that substructure as it sees.
Yeah, so I mean, like, it seems like the complexity is kind of capped. Like, maybe after a certain point, okay, you can add more of this or that, but the fundamental complexity is still not changed.
Yeah. Another comment I can make about this particular problem, which in math is called unknotting problem, is that it's known to be in complexity class NP and co-NP, and it's not known if it's in P. But here I would bet my money, I'm not sure if my collaborators would, that it's probably in P given what we see. So maybe what's happening is that it's hinting at some polynomial nature of the problem, which then we simply, as human, we haven't found polynomial time.
Yes. Questions about it. For every braid length, you are using a different model, or is a single model that is training but all the lengths, or?
No, it's a very good question. So I forgot the details, to be honest. It's very good, but it's in batches. So yes, to make it more objective comparison, so I think what goes, it's like in steps of 20 or something that we because if you of course if you train I don't know on braid length which is 100 or
You
200,
can predict the
yeah, exactly. It should perform just as well on low number of crossings if you had everything by zero. So yeah, so it's different models. That's explained in great detail in the paper, but since it was a long time ago, I don't remember precise.
Okay.
Question. So then when you're testing, how do you obtain the sets of the nodes that you're testing on?
Oh, that's another great question. So yeah, so we produce examples of knots and unknots by taking simple knots and doing this moves and reverse, scrambling them, and so
So
on.
you're doing this at random. So
Uh,
I guess it's done automatically at random.
Yeah, it's done at random, but what's important is that, and then this is also a lesson learned by me in early days, an artifact of not taking CS classes properly. I'll tell you a story, anecdote about it. That it's important to prepare your data set in completely unbiased way. I mean, luckily, CS people are very good at requiring high standards of data sets. And luckily for this paper, it was already known to us, and then we did it in the right way. But the anecdote is that a version of this project I started with Mike Friedman, and we had an intern at Microsoft Research for a summer. And we were basically doing exactly the same thing. We're trying to classify knots versus unknots. And the only thing we did is we created a data set by starting with this object, which is a knot, and then scrambling it by doing this radiometer moves in reverse. And then we took this knot, which is called trefoil, and doing this moves in reverse. And then this was basically our thing. And by the end of the summer, AI or simple ML model managed to learn it reasonably well, and so on and so forth. But then when we started analyzing why, what happens is that there is something where there are very extremely simple polynomial type, quickly to compute invariants of very complicated diagram, which looks totally messed up. And if you need to decide if it's of one type or the other, this invariant is probably what this thing learned, such as signature. For this guy, it's 0. For this guy, it's 3, and that's it. So doing this for the maximum does not change invariant. So that was disappointing because by the end of the summer, intern had to go back, and the project was basically kaput. But it taught me a very valuable lesson that one has to be thinking very carefully about unbiased data set, so that we don't learn the silly things like this. Yeah.
Well, I mean, even with an unbiased data set, could that behavior be due to the fact that due to a phenomenon that something like out of the large number of unknots with n crossings where n gets getting big, like the fraction of the ones that are easy to unknot gets bigger and bigger, but maybe there's still sort of an increasing number of ones that are really difficult to unknot, but just that's a smaller fraction of the whole thing. So you should just sample all of them, and you see more and more that are easy to unknot, basically. But there might still be,
Exactly.
some increasingly large number of ones that are difficult to unknot.
That's exactly what I do these days. That's exactly the punchline of my talk. So that's what I meant by seeing different things on this diagram.
So that's sort of what Ernesto was saying.
Yeah. So yeah, back in the day, I would see that this is 99%. Now, when I look at this diagram, my main focus is what happens here. What happens in this tiny fraction? So what are the hard ones? Unfortunately, we did not ask this question back then, but that's basically where I'm heading. So Nina was suggesting that it would be good to revisit that. I think luckily code is available, everything is available. So if I were to go and revisit, and again, if any of you are interested, I don't think I have time, but I'll be glad to collaborate on this. In fact, it would be good to revisit exactly this 1%. So yeah, I think that would be, we will learn something.
So that 1% could be uncomputable?
Well, that's 1%, which even the good guy, this TRPO algorithm, is not managing to unknot, even though this is meant to be all of the unknots, complicated scrambled diagrams. But Carlos is asking very, very good question. Why is it not unknot? So is this something intrinsically hard about this example? And as I'll try to explain by other similar problems, unfortunately in this project, we were not even set up to answer this question. We were not thinking about it, but our data representation did not allow to ask for it. And one reason is that it may be that to unknot these guys, you have to increase number of crossings from 100 to 200. And back in the day, we were padding everything by only 20%. So therefore, I don't know, maybe.
That's how it is to solve a simple problem, but looking at the big picture.
Exactly. So yeah. So I think that's a very important question. This is exactly the kind of question that I love these days. That's what is interesting in like, trying to fine tune RL to each particular high level research problem. Yeah. So I'll move on to other things, but first I need to tell you a little bit about this different algorithms. This is like
Maybe it's a dimension issue, like it gives them another dimension that they can go through the dimension.
would be
That's why,
yeah. Yeah. So
That's
again,
why it becomes higher on the
Yeah, mathematically,
layer
I
more
think,
dimension.
yeah, mathematically, this 1% contains a wealth of information that we still don't know. Probably super important for knot theory, but something I cannot tell you about because I don't have that vision or knowledge. I mean, it's hidden from us. So that's why it would be good to repeat this experiment. Anyway, so my point is that it's important to experiment. It's important to try. And first of all, off-the-shelf AI. So this talk will be also a crash course on RL algorithms. I promise that this is reinforcement learning talk. That's what it means to play the game. So as you can see, things perform differently. So let's go quickly through all kinds of RL algorithms. So first thing is every RL is kind of a search. It's search on a path between unknot or not, or hypothesis and the goal in theorem proving. So first, it's good to start with a very straightforward type of searches, such as depth first search or breadth first search. So this slide explains what breadth first search is. It's basically where you first explore the levels and then their children sequentially. Depth is the opposite, and then there are various kinds of hybrid searches. This has nothing to do with RL. This is just basic theory of algorithms in computer science. So the first and still popular reinforcement learning algorithm is DQM. So let me quickly decode this thing. It comes from this DeepMind paper, which is 10 years old. Unfortunately, this talk is in 2024, so it's already 11 years old. It's last year was better reference to it. And this is no kidding. This is figure 1 from this very serious paper. And the title is Playing Atari Games with Reinforcement Learning. So one thing it teaches you is that people who do AI, especially who do reinforcement learning, play a lot of games. And that's very true. So when I was showing you this Moonlander and so on, it's not a joke. So the goal here is to basically teach RL from self-play to play these games. Self-play is very important because in mathematics, I may not know anything about Riemann hypothesis. All I just need is to be able to encode the statement and necessary lean steps so that I give machine enough information to go by, but then it learns by itself. So here, of course, this is a great success story. So what is this algorithm? It's based on a very simple learning tactic or scenario, which is Q-learning. So that's even before neural nets get in the game. So basically, you have your state space, your action space, and for such combination of state and an action, you assign a Q value, which is Q stands for quality. For instance, here, if you get on this mine, you die. If you, I guess, get, I mean, this lightning means energy, so this is a good thing, and so on and so forth. You start populating this, the state action matrix with Q values. And yeah, so going back for a second. So neural net on top of it is what gives you Q learning, DQ learning, and then DQM is a further variation of it, which is very similar to DQ learning. There are minor distinctions here between second and third column in the table. These are characteristics of the perform, but there are major changes between first table, which is just Q learning, versus the next two columns. For example, you can see stability, this struggles, this handle well. Generalization, which is important from unseen, from seen to unseen, is also important, and so on. So DQM is very old algorithm. It's based on this table of Q values. And it still actually is pretty good. So I like it because it's much easier to code. Those of us who write code have easier time with this. It's easier to train, easier to handle, easier to tweak in terms of hyperparameters than several other things I'm going to tell you. So this DQN was not even among the options that I offered. I offered two things on that slide. So it was TRPO and A3C. So I'm going to be coming to this in a second. So these are different algorithms. This one is like, again, prehistoric in the modern age of machine learning. Prehistoric means 10-year-old. Things are moving really fast. So what is A3C? This is, as you can see a little later, this is 2016. So I'm also going to walk you quickly through timeline. So this is asynchronous advantage actor critic. So there are 3 A's in the name, and one critic is C. So that's why it's A3C. And the way it works is the following. So you have several, you can think of them, agents or workers, such that they report to their boss and they do things separately. So that's the first thing, asynchronous. So they do it separately. Okay. Then actor critic is basically where actor proposes the steps and critic evaluates them. So that's a class of algorithms. And advantage refers to how we arrange the value function in this algorithm. So it's quality minus the value. So this advantage is kind of important measure. Again, if you haven't seen this before, that's fine. But this explains 3 A's in the name. Asynchronous, the workers, several workers do their job. Advantage is about the value function, and actor critic is just a general name for a class of algorithms where there are sort of 2 opponents. One is proposing the actions, the other is to evaluate. So that's the guy which actually didn't perform well on my plot. But then another useful thing to know is that a year or 2 later, people proposed that you can throw away asynchronous. This happens sometimes, and again, this is usually very empirical and experimental, that sometimes you can take algorithm that works really well, and you can make it better by adding more stuff to it. That was, for example, with architectures going from transformer to reformer. But sometimes if you throw away things, surely you can, I mean, you make it easier, so it cannot be as good, but sometimes what happens, you don't sacrifice so much in performance by doing that. And in particular, if you throw away asynchronous, you get another algorithm called A2C. And the point, which is empirical, is it does almost as well as A3C. But in terms of resources that it requires, it's much better, it's faster. So in that sense, it's a good thing. So it's a good thing to experiment. So what is the trust region policy optimization that was doing really well? That's a completely different type of algorithms called policy type algorithms, where there is a policy network that's trying to make a decision, but unlike the usual gradient descent or ascent, whichever one is used in our network, this does slightly differently, because if your landscape is very rigged, what can happen is that you make step in the right direction, but you may fall and never recover. So this trust region policy optimization, that's the trust region part of the algorithm's name, says, okay, you're standing here, it evaluates what happens in the region near it of a certain radius, think about it this way, and tries to make optimal decision within that region. So this way, you can never have the effect of falling off the cliff. Yes, you're moving much slower. It takes a lot more resources to train, but it's more reliable, especially if your landscape of decision making is very good. So that was important, and this guy worked really well. So this is among algorithms I mentioned. I basically made them in sort of sequence of complexity, and this one is also older because this is from 2017 by Schulman et al.
There was something called Monte Carlo, something or other. Is that similar to that?
Well, there is another one called Monte Carlo Tree Search, MCTS. Yeah.
No, but there was one that was doing Monte Carlo for the training coverage.
Then I'm not sure. I mean, this one would be even more advanced compared to this one. So that's the one which is used in AlphaGo. I had a slide on it, but it's not here.
You can use that.
Huh?
Yes. So a search too. A search that is using the.
Yeah. So, right. So then, yeah. So Schulman and all quickly noticed same thing they saw with A3C. They saw that you can actually remove something. So yeah, TRPO is 2015. So 2 years later, they noticed that you can remove something, and that makes it still a good algorithm. So another thing, like here, you get A2C as a version, which is effective. From TRPO, you get PPO. So this is proximal policy optimization, and it's the same group, but they basically explain that you can throw some things away and gain a lot of efficiency by not sacrificing too much in terms of quality of performance of the network. So again, this is algorithm. That's not like maybe I shouldn't say that. Yeah, so this is crash course on different off-the-shelf algorithms that are available to us. Again, as you can see, even 10 years later, standard benchmarks as to see how they play Atari games. So we love playing games in this business.
It was called Metropolis Monte Carlo.
Okay, so then I'm not sure in what context this is. Okay, so right, I told you about this project. So this is unknotting decision given a complicated diagram. Question is it knotted? So another thing that we tried more recently is a version of this project, which I thought would be analogous, is trying to decide if the diagram like this is slice or not slice. So to computer scientists, this is not much change because instead of 3 randomized moves, you throw one more move called bend addition, and that changes it into this problem. So in terms of RL, it's almost the same. So there is no change. And I thought we would quickly do something good here and so on. But as I want to explain now, this is actually related to very serious math problems. So for example, smooth Poincare conjecture in dimension 4. The usual Poincare conjecture was solved 20 years ago by Perelman, but everybody knew what the answer is. Everybody knew that what looks like a sphere is a sphere in dimension 3. In dimension 4, we actually have no idea. Opinions are split. So in my opinion, this is actually a more interesting version of Poincare conjecture because we don't know. And counterexamples to this smooth Poincare conjecture, abbreviated as SPT4 and many other cool conjectures, they're based exactly on this, like, instead of unknotted, we have to decide slice or not slice. And as I promised, much of what I'm telling you is open source, so you can go to this GitHub, download the code, and again, use it. So it's actually usable for experiments and other questions. And third problem, which I probably will mention very, very briefly in the end, but that's actually more important now, and that's what we're doing these days, is not even from knot theory. This is from combinatorial group theory, which I also thought would be a close cousin of the previous two. But in each one of them, I now try to identify not so much like if it works or what's the success story, but exactly as you emphasize, not that the model can solve generic guy really well, but rather what happens with hard ones. So this is actually what excites me most, and that's what we need to solve really hard math problems.
Are you going to say with slice? It's easy?
Yeah, I'll try. Can I have actually 5 more minutes?
Yes, sure.
I don't know who is the chair. I appreciate all the questions, and yes, so I'll, especially our chair's generosity. So, but first, yeah, let me state a theorem, which is quite well known in the field. And in low-dimensional topology, many people are excited about this fact, so that's why sliceness is important. So theorem says that if you find a pair of knots, K and K prime, which share the following 3 properties, then you found a counterexample to this famous conjecture that nobody even knows how to find. And one property is that, again, it's a decision thing. So every knot is either slice or not slice. So, for instance, unknot is slice, trefoil knot is not slice. And every knot is either yes or no. So roughly half of the knots are sliced, half are not sliced. So first 2 conditions that this theorem is asking is to find one which is sliced, the other is not sliced. So that's extremely easy, they're medians. So then it's also asking that these 2 knots share something in common called zero surgery. An interesting thing is that even if you don't know much about zero surgery, I can tell you that any 2 out of these 3 conditions are extremely easy to satisfy. There are millions and millions of knots, we can write it immediately, which share the same surgery, and one is slice, or one is not slice. So that's not a big deal. So there are lots and lots of them. The question is, can we have all three together? So that's again a good decision problem, very much like unknottedness or unknottedness. It's like yes or no decision problem. So what is it asking? It's asking that if there is a knot, so here it's like looks like a knot, but think about some complicated knot. It's asking that there is topologically a disk, a smooth disk in four-dimensional space that bounds it. So that's what slice means. And the definition refers to four-dimensional space. That's why this question actually knows a lot about cool things in four-manifold topology, smooth structures. That's why it's related to Poincare conjecture and other things. So this is yet another conjecture called slice ribbon. It says that every knot which is sliced is ribbon. This was proposed by Ralph Fox 60 years ago, so it qualifies for this long-standing conjecture kind of that I'm looking for. And ribbon means that in four dimensions, this disk, the way it's shown here, is such that with respect to natural Morse function, which is radial function, there are no maxima, so there shouldn't be this step here, but it would be saddles or minima. So that's called ribbon. In conjecture, it's easy to see that every ribbon is obviously sliced because that's a stronger notion, but conjecture says that the converse is also true. Okay, so both are interesting, both are non-trivial, and we have no idea how to approach these conjectures, but there are lots of potential counterexamples. And this is a fairly recent one from Tom Schauman and Thompson, who constructed whole infinite family. And the smallest member in that family that we don't know whether it's slice or non-slice is this with 50 crosses. So this illustrates that we need something powerful. But as a quantum topologist, when I joined this field, I was working on various invariants which try to abstract sliceness and so on. And we were stuck here at roughly between, I don't know, 10 and 16 crosses. I never did calculations by hand or even with traditional computers before, which would venture me out of 16 crosses. It's just impossible because complexity here grows exponentially in number of crossings. And that's pretty bad. So yeah, that's why we quickly grow from 100 to 10 and to a million of prime knots at 16 crossings. And what we need for all these interesting conjectures is be in this range, 50, 100, and even more. So therefore, there was a huge gap. And because the complexity grows exponential in number of crossings, this is pretty sad because even with Moore's law, even if computational power of traditional methods improves by a factor of 2 every couple of years, it means that to go from 16 to 17, I need to wait a year. So then from 17 to 18 and so on, it means that if I want to be here, I need to wait 50 years. And I'm not sure I can live that long. So that's why I need new tools, because that's an exponential scale. I'm going to skip this slide. Yeah, so we did the same thing. We tried to train AI or various neural nets. You can see here familiar words, hopefully familiar by now, A3C. We actually tried TRPO. It didn't work as well. We tried Monte Carlo research. It didn't work as well. So sometimes what works on one problem does not work on the other, and so on and so forth. That's why it's important to experiment. But another thing, and again, you see this graph, which in old days I would interpret as a success story because you train it and then something approaches 100%, that looks good. But now I interpret this as generic thing looks good. But what about this 1% for outliers that don't look? Okay? So in particular, yeah, so performance actually here, and this problem is more pronounced. So performance here was not as good on the first problem. So I wouldn't say it's easy for AI for some reason, even though it's completely analogous. So you can see that things actually dropped from 100% to 30, 40% as number of crossings improves. We did learn something about concordance. I'm gonna skip that part, but that's what I'm trying to get to. There are nodes sometimes of very small complexity. So this is only 18 crossings. This is not 100 range. This is just 18 crossings. And here we couldn't decide if these are slice or ribbon or not. So at least our RL couldn't do it. Even though it does really well on generic examples with this number of crossings. And these ones are particularly interesting because these are from paper of Ciprian, who was on this work, Ciprian Manavescu and Lisa Piccirillo, as leading candidates, or at least at the time, to counterexamples of smooth Poincare conjecture. So this is actually what you want to know. And surprisingly, what's interesting mathematically turned out to be difficult for RL. So maybe, I mean, on generic examples, it did really well, especially in this range of process. But on examples where we do care about, we didn't. So this basically, a year ago, initiated my whole research into, okay, let's focus on hard examples. So what makes them hard, and so on. And now, so yeah, that's why I give the same summary slide. So there are several projects, and by now I did many more. But now I look at what makes it hard. So unfortunately here we didn't even ask the question, but you guys did. But what makes particular unknowns hard? I don't know. I mean, we didn't have tools to answer. So here it's extremely important because this sliceness and ribbonness, this is directly related to all these tool conjectures and topology. And again, there are analogous problems in algebra and various other branches. And in particular, more recently, so hopefully the paper will appear in about a month or so, and applied it to Andrews-Curtis conjecture, which also I thought is just a variant of all these other problems. In fact, many people consider them very similar. But this one really brought everything home. So this emphasized that hardness is not just something that we can ignore or consider as interesting in addition kind of question, celebrating this 99%. No, this is actually very important to this particular problem. I'm not going to tell you what Andrews-Curtis conjecture is. It's about relating trivial presentation of a group to non-trivial presentation. But you can think about it as relating trivial knotted diagram to non-trivial knotted diagram. It's basically algebraic version of that. And you also have only 3 moves. So we're talking about very small action space, 3 basic moves. For RL, this is vanilla thing. You have huge configuration space, couple of moves, very easy. But this is a mathematical theorem, and this is something not to snooze. So only less than 10 years ago, but now there are several versions of this theorem, say that you may have very short presentation of length n of this trivial group, which you know is relatable to the trivial presentation. But number of steps is hyper-exponential. So it's basically 2 to the 2 to the 2 and so on n times. So the fact that when we were doing a knotting problem, we only padded by 20% is a joke. Even if we pad by 2000%, this is not enough for this. So how on earth RL can find, for example, this is a very short presentation, but it requires 10 to the 10,000 steps. Okay? So this is what makes it hard, and this is now where the fun begins. So how do you solve this with RL? So that's basically what we're studying, and again, I hope there will be another occasion to tell you more about it. But I want to emphasize now that, to me, the coolest thing is exactly this kind of hard cases. So if you can ask me privately, or maybe I'll tell on another occasion how we try to overcome this. It's actually a lot of fun. So this is where algorithmic development really begins. That's where we try to solve hard problems. But now, I want to emphasize that this is very different. I started by saying, look, all these RL problems, it's like playing a game of chess. Okay? Can you think how on average, professional game of chess, how many steps in a given game, how many moves does the opponent make? You know?
It depends what is the type of game.
Well, suppose like championship or even in Blitz, it's very
Less 3 minutes is 24 or 36, something like that.
Yeah, it's I mean, usually it's in the range of 30, 40, so that's how many moves a game of chess takes. Okay. So, and variation is very small. The longest recorded professional game has 300 steps, well, 269 to be more precise. It happened in Belgrade in 1989, okay? So variation is very small. So chess, yes, it has more moves, but number of moves overall in a game is tiny. So if you want to reward something and discount it properly, it's for RL, that's extremely easy. On the previous slide, I was talking about 10 to the 10,000 moves. So this is nothing compared, like a game of chess, this is a joke. Because you have to discount something. And if you want to win this kind of games, that's what actually may be needed for even hypothesis. If we go from H to G, it may have a lot of steps. So we need to have RL algorithms to know how to find these complicated paths, discount rewards, and so on. So this becomes actually fun RL or ML project. And now the reason I'm giving this talk is I want to use it as an advertisement. So recently at CalTech, we started a whole new initiative to make it a hub of mathematics and machine learning. So we have partnerships with Silicon Valley, and therefore, if you want to come and work with us, so we'll be splitting time. We have a lot of resources. In particular, if you know anyone who might be interested in applying for postdoc jobs or other jobs, please send them to us. And if you like this kind of research, basically finding needles and haystack using reinforcement learning, that's what we do. Thank you for your